Hello, everyone. Good morning, Europe. Good afternoon, Asia. My name is Sven Philippe. I'm a structural geologist at Eliis here, and I would like to welcome you this morning for this e-class about the presentation of a new geological time model in PaleoScan that we named structurally consistent. We're going to start the presentation in a few seconds. I'd like to just leave my mate, Benjamin, get to introduce himself.
Good morning, everyone. My name is Benjamin Duro. I'm a geologist working at Eliis, so I've been using PaleoScan for the past 8 years now. And I'm going to be the one helping Sven with questions and chat. So if you have any questions, just feel free to ask. Thanks.
So your question ought to be addressed either on the chat. In the chat, your question are going to be public, so everybody can enjoy your question. And if you want to ask a private question, just ask it in the question chat in the question channel. So let's get started. We're going to turn off the camera just to go for the presentation. So I'm going to start this presentation with a few slides of a PowerPoint, just for you to get the concept of this new type of geomodel. So I would like to start it with a brief recap on the global workflow of PaleoScan so that you know what we are considering in this presentation here. So here's the general workflow in PaleoScan. I'm just going to activate the pointer for here. So we're starting in PaleoScan with the input of several type of items, classically the seismic, that is going to be the main data that we're going to use, and some constraint items or some reference items like horizons and faults, for instance. And then in PaleoScan, the core part of the process for now is going to be the interpretation of the seismic in order to give a good amount of constraint to be able to generate what we name a geomodel, or if I want to be more precise, I would name it a relative time geological model. So to make it simple, I will just name it for the session geomodel. And this geomodel in the PaleoScan workflow is a key part, because if you end up with an accurate geomodel, with an accurate geometry regarding the geometry of the geology, then you'll be able to generate a series of output that is going to be consistent as well. So for example, horizon stacks, so dense series of horizons on which you are going to be able to consistently map your attributes, and for example, derived attributes, such as this volume of thinning in PaleoScan. And then down the workflow, you're going to pass it on to the reservoir engineers, create some static models into PaleoScan, and pass it on to more adapted softwares. So for today, we're going to focus on we're going to focus on here in the model grid and the geomodel generation. So traditionally in PaleoScan, we're using what we name a classic model. This model accounts for all existing and automatically propagated and manually edited horizons in the grid, such as you can see in this tiny picture. We've got the marked only type of model, that is using only the marked horizons to build the geometry of the model. And what's new in PaleoScan 2020 is the marked only faulted geomodel. And as its name suggests, this type of model is going to be built on only the interpreted horizons, the marked horizons, and as well the faults. So let's get started for these recaps so that you can see the differences in the different processes. So we're starting with the seismic block, which in this case is the XML block from the Carnarvon Basin offshore Northwest Australia. You can see the seismic, and on top of the seismic in PaleoScan, we're going to start interpreting in the model grid. So the model grid is going to be the framework of the interpretation. And then you see in color all the marked horizons. So these are the horizons that the interpreter would have interpreted and potentially edited manually. And based on this, plus all the automatically connected part of the reflector, so all what PaleoScan has been automatically interpreting, then you can see in this image some links in between some nodes that are going to be propagated along the reflectors of similar polarities. Then based on this constraint, we can build a model out of this geometry. So what you see now is just a preview of the model on the grid. But already in this preview, you can see there are a few flows in the geometry of the future model. So for example, you can see some geometrical discrepancies here and there. And due to the presence of faults in this lower part of the seismic, then you may have also some thickness variations that shouldn't be here, and some tiny bubbles here and there that you'd like to improve. So to try to improve this, we've created a second process that is the marked only geomodel that only accounts for the marked horizons, so the colored horizons in here, to determine the geometry of the model. So if we're considering this, we are only considering this amount of constraints, so the marked reflectors, and PaleoScan is going to use the vertical relationships in between every available marked reflectors, so marked horizons, and is going to propagate laterally the geometry of these reflectors with the thickness relationships based and relative to the other available reflectors. So we've got 3 examples here for 3 different horizons in the grid, but if you're doing this vertically everywhere on your volume, you end up with a geomodel that is going to look like this. So again, we're considering a preview here. It's not the final model, but now you can see that the geometry of these models is going to be more synthetic compared to the one that we had before. And the issue is, although it's more synthetic, then we still were not necessarily everywhere respecting the geometry of the actual seismic that we can see in co-rendering in the background. Plus, on top of this, we're still suffering from vertical artifacts at fault location that are not taken into account. So to improve this again, we've created this marked only geomodel with faults, and we're taking into as constraints all the marked horizons only, so that the interpreter can have a huge control on the selection of the reflectors he wants to consider for the geometry of the model. And on top of this, if you've got a fault set available, as symbolized here with the red intersection, then you will take the geometry of the faults, these structural discontinuities, to constrain the geometry of your model. And with this, you can expect to create some structurally consistent geomodels, such as the preview that you can see here. So again, here, I'm going to comment very briefly because I'm going to go into the PaleoScan interface to show things on live just after. But you can see that we're able to follow more nicely the geometry of the seismic, and we're respecting the we're more consistent regarding the displacements at the fault locations. And it's kind of a bonus, we can also manage the thrust structures. So we can manage on the model the multi-Z relationships if we've got some compressive regimes, for example. So again, this is an example of just a marked only geomodel here. So you've got some faults, but their geometry is not accounted for. And if you're stepping into the marked only geomodel with faults, this is the type of result of model and the geometry that you can expect. So again, we've got a nice listric faults done there that is going to be played in compressive tectonics. So we can have some thrust structures. And one last point, just to be clear on this. So I've said that the geomodel can be created in managing the multi-Z relationships. This is what you can see in this top picture here. But for now, in this version of PaleoScan, you cannot directly create some items such as horizons, horizon stacks, for example, with multi-Z structures. You're obliged to convert this multi-Z model at this point, so that to get rid of the overlap, the vertical overlaps, and create your items. So now I'm just having a look at the chat to see if there are some questions that should be addressed. I see that they are none for now, so I suppose that everything is clear. And then I'm going to go for the live demo into PaleoScan. So here is my PaleoScan interface. I'm going to introduce and to show the examples of what I've been introducing in 4 different example projects very quickly, and how you can benefit from this new type of structurally consistent model in here. So the marked only with faults. I'm going to start with a tiny seismic volume that is going to be in New Zealand. It's the TUI block. I'm not going to show you like geological introduction about this. I want to be quick on this and directly show you the model grid interpretation framework and the use of like a good interpretation for building a multi-seed relationship and a multi-seed geomodel building. And we're going to compare the two building of a classic model, like I showed you in the beginning, so the one that is accounting for every available connections in the grid, and the multi-seed with faults. So here, if I'm zooming in a bit, you can see a pretty simple layer cake structure deposition. And if I'm activating the default model in my properties here, sorry, I'll try to make it bigger this way. So you see that the quality of my model is medium, and this corresponds here in this case to the classic model, so the one accounting for every connections that PaleoScan would have automatically made. And on top of it, if you've edited the horizon, it will also account for the edited horizons. So what you can see here in the seismic, for the top of the seismic, where the reflectors are quite continuous, are quite nice, then PaleoScan is able to generate a structure of geomodel. This is only a preview at this stage, but PaleoScan is going to be able to create a model that's going to be quite consistent. Now, as for the bottom part of the seismic, that is more chaotic, with more discontinuities and artifacts as well. You can see here slanted reflectors that are just artifacts. Then PaleoScan is going to struggle to create a consistent geometry in the model. We're going to see some lateral gaps. And if I'm scrolling through, you're going to see some inconsistent thickness variationships in the model. So I can go quickly through. And I'm not really happy with this, and I don't have time to manually refine everything to make this thing look nice. The issue here with this model is that PaleoScan is going to here and there catch these artifacts, and it's going to create some links, as you can see here if I'm zooming in, that are going to be following the polarity of the artifact, and this is going to corrupt or to introduce a bias in the geometry of the geomodel that is going to be built. And this is quite annoying, and we don't really want this to happen. So instead of this, I'm going to try to take advantage in my interpretation of the marked only faulted geomodel. And in this case, we don't have any problematic with faults, so it's just going to be a rough interpretation where I'm going to mark the most reliable and the brightest reflectors. So I'll do it quite quickly here just for the example. So let's go for a bit of interpretation. I'm not saying what I'm doing is going to be perfect. Okay, I'm just going to make sure to give some main constraints for my future model. So here I've got two reflectors, one maybe for the top of my chaotic interval and one for the bottom part, where I can see some kind of brighter reflectors. And only from this point, I'm going to switch from the classic type of model, of preview model, to the marked only faulted model. So the one that is supposed to be structurally consistent and only using the marked horizon plus the faults, if any faults, to determine the geometry of the future model. So it's pretty basic. It's just a bit of computation here to display the preview. Okay, I'm going to show you the real model in the end. And here's the type of geometry of model that I'm going to get. So of course, it is going to be very basic because I've just set two horizons in my interval. I could add more and refine the geometry of my model. So here you see a slightly more advanced interpretation that I'm going to open and to show you the improvement that you can get by just marking a few more horizons in your interval, and that these few more horizons are going to have a very positive effect on the improvement of the geometry of your marked only faulted geomodel. So we're loading a new interpretation. Here we go. So you see I've got only a few more marked horizons in this case, not many. I just caught the reflector and interpreted the reflectors that seems more obvious to me in this chaotic interval. And based on this, you can see if I'm just going through that we're going to be respecting the global or the main geometry of this interval. And we're going to be able to get rid or to discard the effect of the artifacts. So if I'm just displaying the global model again, is what my global model is going to look for. Okay, for the top of the seismic, I'm not looking to use this model. As you will be observing in the future, we can do some hybrid geomodels that are going to be able to benefit from the classic model, taking into account every possible horizons for the top of the seismic here, and just taking into account only the marked horizon for the bottom part of the model, just not to waste some time trying to manually refine every tiny missing connections or correcting from any wrong connections that are going to follow the artifacts. So that's one first example. I'm going to switch for another project to show you something that is getting also interesting in regard with this new geomodel that we have, with this new type of geomodel. I'm remaining in New Zealand here, staying in New Zealand, and I'm going to show you another grid. So with just the basic of PaleoScan is doing automatically. We're going to start from this. And then, as you guess, just later on, I'm going to switch to more advanced interpretation. We're going to start with the beginning. Don't hesitate to ask questions in the chat. Benjamin is here to answer them along the presentation if you need them. If there is something that comes up at the top of your mind, don't hesitate. So again, just as an information, this webinar, this e-class is going to be recorded, so it's going to be available on demand at the end of the session. Okay, so here we go with a new type of seismic. Just going to adjust the vertical aspect so that we can zoom in a bit and see things in there. So there's another type of seismic, and I would like to go into a specific problematic location here where we've got some potential injectites here. So you can see that there's these bright reflectors that would correspond to injectites. It could be a similar case as for igneous intrusions, for example. So similar type of relationship with the sedimentation, where these injectites is going to cut across the sediment deposits. And due to the bright reflectors that it creates, if I'm displaying the classic type of model preview, that is accounting for every available automatically propagated reflectors, then I'm going to get aware that I'm going to have some weird thickness relationships laterally, and I'm not really satisfied about this. So I could try to refine this to improve this. Let's say, okay, so I'm going to try to improve this. Say, okay, I want to correct from this, but you're going to see that it's not as obvious as this. So maybe I'm going to just mark these through horizon. For example, in here, I'm going to have to force PaleoScan to recognize that this piece of horizon is a proper piece of horizon that should be connected to the yellow marker, the yellow horizons that I'm interpreting right now, just to improve the thickness relationship that I will create in the geomodel. So I'm not going to do many horizons, just for the example. Okay, 4 horizons, and I could do maybe a 5th one. So for example, here, just to make sure that this tiny horizon here has been accounted for. And then I'm going to return to the preview of my classic model and see what change I've manually induced. So I'm going to display the model itself, and you see that although I'm trying to manually edit these horizons, that I'm still suffering here and there for thickness thickness like a bias, let's say laterally, due to the presence of these injectites that are connecting through. So if I'm looking at the grid here, I'm going to see that I've got some wrong connections. So it depends on the brightness of the reflectors itself. But I see that I have some wrong reflections that are inducing some bias in the geometry. And if I don't want to spend too much time editing manually my horizon, then what I can do is that instead of the classic type of model, I can play with the marked only faulted geomodel that is, again, only going to be accounting for the marked horizon and the faults, if any. So again, in this seismic, I don't have any faults, so it's not going to be included in the constraints. But as you can see, it's pretty simple here. I'm just going to hide for a second my reflectors and just display the isoline preview of the model. That is the equivalent of the colored layers that you've seen before. Just here, I can just grab any individual value of the preview of the model, and you can see that now my geometries are quite consistent to the geometry of the deposits. So it's going to be better. And if I'm moving to more advanced interpretation, let's say this one, you're going to see that with the marked only interpretation, that we can really have some nice results in terms of preservation of the thickness relationship laterally in the seismic. So in here, we've got only a few injectites, right, here and there. So locally, they're disturbing a bit the interpretation, but we may have some cases. I'm thinking, for example, in the North Sea around the Western Shetland Islands, some huge amounts of igneous intrusions, for example, that are going to be with PaleoScan drastically disturb the interpretation, because PaleoScan is going to automatically catch the bright polarities of your igneous intrusions, for example, and really like make a mess of your geometry. So now again, so sorry, I'm gonna have to display the horizons to make a more accurate display of the model, but see that I've marked more horizons in this interval here, and I can expect from the marked only faulted preview of the model to have more consistent thickness relationships around here. So again, hiding the horizons, you can see with just the colored layers that the geometry is going to be much more consistent with less thickness variations. If I'm just playing with the isoline, this is also what we're going to observe. So I'm just hiding again the horizon just to have the isoline. And you can see here that I'm following my reflectors very nicely and very neatly across and inside the injectites. Okay, so when you're doing this, if I'm just showing you the output of the actual model, because right now I was just showing the preview. I need to change this and save it. So I would like to just show you the difference in the two types of models. So I'm going to use a blender here to blend the initial data with, for example, the classic model. So the model I'm injecting here is the classic model, accounting for every possible reflectors that are automatically connected by the PaleoScan. And on the side, I'm going to compare this with my marked only model. So I'm just going to arrange these two viewers so that we can see them side by side. I'm going to synchronize them. Okay. I'm just going to also adapt the vertical scale so that I can zoom in a bit more. Here we are. And I'm going to be back at my injectite position so that you can see the output of this model where I've got the injectites and see the difference between the classic model and the marked only. And you can already see this, okay, if I'm just removing for a second the display of the classic model. So you can see one injectite here, for example, second one here, and then a tiny one here towards the basement. And so if I'm showing the classic model again, you're going to see that again, we've got some thickness discrepancies here where we've got the injectites. And if you're comparing the same position that is synchronized here in the viewer at the bottom, then if I'm pointing to these thickness discrepancies, you can see that they're very absent. They're actually absent in the geomodel that was created only with marked horizons. And this is kind of an advantage that we have if we're using the marked only faulted geomodel. And on top of this, just to really prove that that we've got some nice advantage doing this, of course, if the geometry of your geomodel is accurate, then when you're going to create, for example, horizon stacks and mapping some attributes on the horizons in the stack, then you're going to be able to benefit from this relationship. Okay. For example, here, you're going to see the difference. So what we have here, so is the classic type of model to the bottom left, and to the bottom right, we've got the marked only model. And for example, if I'm scrolling through, so I'm just going to select the classic viewer here so that it appears, its intersection appears red in here. Then you're going to observe that if I'm synchronizing the position, that the geometry, of course, of the classic model is going to be biased due to the biased geometry of the geomodel itself, whereas the geometry of the classic of the model, the marked only model, is going to be much more consistent in this interval with the injectites. And I've mapped the RMS amplitude in these two viewers, and you can see that if I'm looking inside the injectites, then I'm going to have a more consistent mapping of the attributes due to the fact that I'm respecting the geometry of the deposits, and I'm not influenced by the injectite crossing across the sediment deposit. All right, so I'm going to move to next case. So I'm going to quickly move to a case. It's F03, so it's a block offshore the Netherlands in the North Sea again. And I'm going to show you another application or another use of these marked only faulted model. And I'm going to show you this. Just going to pick up the proper interpretation, let's say on this model grid. So again, I'm starting with a raw interpretation where we'll only see what PaleoScan has automatically propagated. Time for loading. I see that there have been one question. So keep going with the questions. Don't hesitate if you have any. So here we're in F03, and in F03, I've got one particular thing, is that we've got some bright spots towards the top of the seismic. So here about the clinoform interval. And now the issue with these bright spots is that due to the bright amplitude, the high amplitude that they have, we've got some artifacts vertically below these bright spots. And basically, if I'm just, again, activating the preview of the classic model, then you're going to see that we're going to have some discrepancies here and there due to the lateral change in the polarities that PaleoScan has poorly managed. See, the issue in PaleoScan is that PaleoScan is very efficient at automatically generating some geomodel based on the automatic propagation, because the automatic propagation follows the polarities of the reflectors. But now, if the polarity of the reflectors is suffering from a tuning, for example, tuning effect, then depending on the correlation threshold that you've used, and this is a bit of a technical parameter I'm talking about here, it should be worth all the session for e-classes. But if there is a tuning effect, PaleoScan would not necessarily distinguish this tuning effect if the polarity doesn't change, or if the amplitude signal is not laterally changing quite significantly, sorry. And then PaleoScan is going to keep propagating, although we're changing in the nature of the reflector. So we can, for example, in the case I'm going to point here. So here we're going for reflectors that pertains to a classic deposit. And we're going to keep going with the same polarity of reflectors, but we're laterally changing. And here we are inside what can be an artifact or bias in the geometry due to the presence of a gas effect. And PaleoScan will not necessarily distinguish this. So when you're displaying the classic model, then PaleoScan is going to go through, and at some points you may have some discrepancies with a preview of the classic model. So what we can try to do to prevent this is using, again, the classic model. So using a few constraints, whether we think the reflector reliable and not suffering from a bias due to these bright reflectors, due to the bright spots. So just marking a few reflectors. Again, I'm not saying that what I'm doing is perfect, is really rough. I'm going to constrain my geometry above these bright spots, and if possible below, even though here below I'm going to jump into an interval that is going to be corresponding to the propagating system. So the geometry is going to be changing and not necessarily as easy. And just with a few reflectors like this, I'm going to display a preview of what would be a geomodel only constrained by the marked horizon and the faults. As you can see here in this case, we've got some faults. So here we've got a regional fault that is kind of wrenching in two pieces at this location. And I'm going to display the preview of the model that is going to correspond to this marked only faulted model. And right here, just with a few reflectors marked and the faults, you can see here that we've got some much more synthetic geometries, and potentially they're going to discard this lateral change in polarities that are going to be related to the presence of the bright spots and to the artifacts that are vertically below these bright spots. Potentially, in terms of model, we can expect something nicer than just with the classic model. Again, I'm going to compare and be back with the classic model. And you're going to see the difference. Here again, this is the type of model that we would end up with the classic type of model. So you see, we would still suffer from discrepancies if we're not refining manually further this interval here. As for the rest of this model, the classic model is doing quite a nice job. So again, you see the value of this marked only faulted model if you've got some specific lateral change in polarities that are due to artifacts, due to injectites that are going to cut across the stratigraphy, the sediment deposits, for example, or this kind of structure here with artifacts that are due to a bias underneath a bright spot. Or it could be the case with, for example, a coal deposit. If you've got some coals, then laterally the polarity may just change locally, and PaleoScan with the classic model will just make a vertical shift at some position because the polarity is going to be changing, and PaleoScan is going to try to laterally follow the same polarity. So I'm going to go for a last example where you're going to see the influence of the faults and the real benefits on the fault geometry, of the geometry induced by the faults. So I'm going to go and open a project that is going to be located northwest offshore Australia. So it's the Exmouth block that I'm going to switch to now. And again, I'm going to directly open the model grid. I'm going to open the auto interpretation. So just plainly what PaleoScan has been automatically propagated and connecting in the grid. So here we are. Again, I'm going to go for a few adjustments here. So this is the model grid of PaleoScan up there again. And this is the classic model that PaleoScan is going to be able to build based on just the automatic propagation. So here at this stage, there is no manual refinement. And just basically what we can observe here is that on the top part of the seismic here, we've got some very continuous and pretty reliable reflectors. They're like the seismic amplitudes, the signal amplitudes is really continuous laterally. So PaleoScan is able to very properly catch this in the grid, in the connection in the grid. So I'm just going to show the grid for a second. See, you've got some nice connections in here. So we're providing already, like by default, a very good constraint for the definition of the geometry of the future model made by the classic model. So accounting for every of these relations of these links that you can see here. But, however, if I'm looking towards the bottom of the seismic, we're suffering for poorer connections due to the presence of faults, again, so normal faults cutting through the model grid and preventing from connections. So again, I can just display the grid again. See that we've got a lot of missing links due to either faults going through the seismic. So because when we created this grid, we've included these faults, okay? We've got a fault set available here, and I'm just going to display it for a second. And the fault set that we've included when we build this grid is going to prevent PaleoScan for creating some automatic connections and propagation across the faults. Okay, you've got these faults here. And due to these severed connection, then PaleoScan is going to miss some correspondence across the faults. And this is why you've got some gaps in the future creation of the model at this stage. So we've got two choices at this stage. We can either go for a drastic interpretation of this faulted interval manually, or we can try to benefit from the automatic for the creation of this marked only faulted geomodel that is going to be structurally consistent. So what I'm going to do here, I'm going to move to a state of the grid that is going to be slightly more interpreted. And we're going to observe first the difference for the classic model, see if further interpretation in this faulted interval has improved the geometry. In this case, I'm just going to, again, to hide the faults for a second, just to have more visibility in what we're having. I'm also going to hide the preview for now. So this is the amount of marked reflectors that we're having here, okay, so that have been manually just marked or refined. Okay, and this is the type of classic model that we're having out of this. I'm just going to hide the marked reflectors here. And you see that Even though we've marked a lot of reflectors, we're still suffering for gaps here and there, and we can even have some discrepancies in the geometries of the model. Here are these locations, because in the background, we don't have any marked reflectors with high and bright amplitudes to follow and to mark with enough confidence. And it's the same case here at the bottom of the seismic. So either because we're losing some amplitude signals due to the fact that we're going more in depth, or maybe because we're in a carbonate interval. And when I'm displaying the model, due to this, you can see that the geomodel is going to be very gappy in this part. It's going to lack a lot of volumes, a lot of areas. So now with this, again, I'm going to show the marked manually edited horizons. And this horizon just has to be marked, okay? So you just pick one that PaleoScan has been automatically creating, and you just mark it. And if these reflectors deserve and need some more refinement, that you can perform more refinements by connecting these reflectors, for example, across the faults. But you can just simply mark them, okay? You can just go and pick one up and say, okay, I'm just going to mark it so that PaleoScan can consider this one in the constraining of the geometry of the future model when I'm going to switch for the marked only faulted model, so the one that is supposed to be structurally consistent. So again, you can observe when I'm turning this preview on, marked only faulted, that some faults appear in the seismic. So these structural discontinuities, these faults, are the faults that we've included at the creation of the grid. So now they are displayed so that you can observe how PaleoScan is going to use them to constrain this marked only faulted geomodel. So let's go for the preview, and we're going to see the difference that we have compared to the classic model. So here we've got a lot of constraints, so this is why PaleoScan is going to take a bit more time to get the preview. I need to activate this preview now that had been computed. And again, for the sake of the visibility of this model, I'm going to enlarge this, and also I'm going to hide the marked horizons, okay? So here is the type of geometry that we can expect from this type of model. Again, here we're looking at a preview, okay? So it's just what PaleoScan is about to do. This preview is, because of the computation time that it requires, is only available on one given line at a time. So you need to scroll and recompute the preview if you're just going and scrolling to another line. But this is the kind of consistency that you can expect. So if I'm zooming in, already you can see that PaleoScan is going to create some very synthetic geometries based on the geometry of the marked reflectors only. And at the fault location, PaleoScan is going to be able to create a neat displacement following the geometry of the faults. And here you can see that we're much more respecting the structural consistency induced by the faults. So this is something that is quite interesting. And if I'm looking at the bottom part of the seismic, remember the one that is suffering for low amplitude reflectors, then even though maybe the geometry is not perfectly accurate and would need some more refinements, then we see that the geometry is much more consistent than before and is much more complete over the whole volume. Okay, before we had some gaps, plenty of gaps everywhere, and now we've got some complete volumes. So again, I'm just going to switch to the ISO line, which is the exact same type of preview, but just displaying one ISO depositional time value at a time. And you can see that when I'm going to go into my faulted interval, I'm going to respect my fault displacements and the geometry based on the markers that I've marked. Okay, so now I'm going to switch to the geomodel that has been outputted. And again, we're going to observe the actual differences that we have between the classic model and the marked only faulted. So again, I'm going to open a viewer, a blending viewer. When I'm going to drop the seismic, I'm going to drop the classic model, and the one without faults is going to be better. And on the other side, I'm going to open just the marked only model. So in this case, I'm going to take this one, which is more advanced. try to synchronize the two. And again, we can observe the differences now in the two types of models. So what we observe, again, this is the seismic without the co-rendering and the classic model on top. Here we can observe for the classic model that the geometry of the seismic is very well respected for the top of the seismic. So again, where the reflectors are quite continuous and quite bright. And now if we're going to the bottom of the seismic, where the faulted normal faults are impacting the deposits, when we can see that the model is not too bad actually, but we can just observe that here and there we've got some thickness discrepancies here, like this one. And at the fault location, we just have a smoothing of the geometries that is being done. It's not necessarily geologically absurd, but it's not really geologically very satisfying sometimes. And we see again that we've got a lot of thickness variations and discrepancies here and there. Although we've, as you've seen in the model grid, we've marked plenty of horizons, right? And now if you compare this position with the model that is at the bottom, so the model that has been outputted accounting for the faults and the marked horizons, then we can see that we're much more respecting the structure of the deposit and the geometries. Again with the seismic, I'm just trying to follow one reflector, for example, so this one here, you can see in the model to the bottom that I'm going to strictly follow the same color in the geomodel, the same colored layers. And again, I'm just going to show you one example of output that has been generated with the two type of models, so with the classic and the marked only faulted, on a horizon stack. So I've got plenty of horizons in there. I'll take the example of, let me check, classic model for the bottom part of the seismic, so the faulted interval. I'm going to open this one, and I'm going to do the same job for the model that's been created with the multi-Z. So again, I've got my two type of models down there. I'm going to reframe this again. So my two types of horizon stacks created for the two types of models. So respectively, you're going to have to the bottom left, the one I'm going to select in red, the horizon stack that is derived from the classic model, and to the right, the geomodel that is derived from the marked only faulted. So again, if I'm just scrolling through the seismic, and you can see the intersections of the two horizon stacks, the one in red, so for the classic, and the other in yellow for the marked only. You can observe them in the seismic, and I'm going to scroll through. And the result of this is that normally, if you're observing the classic, the marked only model, you may have in this faulted location more consistent mapping of your attribute, because the geometry, of course, of the geomodel is going to be more consistent with the geometry of the geology behind. I'm just going through quite quickly. Sometimes, due to the distribution, the difference in distribution of the two horizon stack, I may not see the same part of the horizon at the same time. So here, for example, you see that the marked only horizon is going to be in yellow here. It's going to be quite straight across the sediment, even though it's not strictly respecting the reflectors here and there, where we should have maybe added a few more constraints. But you can see that the red horizon stack from the classic is suffering from much more jumps in the geometry. Okay, here we've got some nice channels, and for this example, we can see then both type of structures. Okay, so I'm going to stop it with the comparison. And now one final point about this live presentation. I've opposed in this presentation the creation of a classic model to a marked only faulted type of model. So another thing is you don't necessarily need to oppose them all the time. You may have some use of one type of model from one vertical interval of your seismic, and prefer the other method for the other part of the other vertical part of your seismic. So this is precisely the case in this seismic, and I could consider creating an hybrid geomodel that is going to be based on the geometry of the classic model for the top of the seismic up there, because my classic model is going to be quickly catching all the subtle things, subtle variation in the geometries of all these reflectors. Although for the marked only faulted, I would need to mark manually a lot of horizons to do so. But as for the part of the faulted interval, then I've seen that my marked only faulted geomodel is much more performant. The interpretation is going to be quicker if I'm creating a marked only faulted geomodel. Then I can combine the two types of model to create something. So this is what I've been doing by combining two types of horizon stacks. So, and I've created like a hybrid model. So I'm going to show you this hybrid model. So this is the one here. I'm just going to clear up these two horizon stacks. And I could also show this hybrid model in co-rendering here. Okay. And in this example, you can very nicely see the difference, the limit in between the two models, because the two models have been created from the classic on the top, from a cropped seismic, and for the bottom, for the marked only faulted geomodel, it's been created from a model grid that wasn't cropped in here. So you can see laterally that the extent of the model changes. But anyway, you can see that vertically, we've combined on top a classic model here, and on the bottom, we've used the marked only faulted geomodels. And if I'm playing with the co-rendering here, you can see that we can benefit from two performant geometries that are going to be very, like as much as possible, accurate to the geometry of the seismic. So I can scroll through, of course, and check at my models in the different part of my seismic. And this is where my presentation is going to end for the PaleoScan interface. I'm just going to return to the PowerPoint presentation for a second. And if we've got a few minutes left at the end of the presentation, more questions are going to be welcome. I'm just going to recap what we've seen together in this session. So concerning this new type of geomodel that we've created in the version 2020 of PaleoScan, the first benefit in there is what we've seen in the last example in Exmouth, is that we're able to create a geomodel that is going to be only accounting for the marked horizons. So implying the fact that you can have, as an interpreter, more control on your geometries, because you're going to select only the most accurate and most relevant reflectors, the ones that are the more reliable. So it can be the brightest, for example, if you're considering the interpretation of a carbonate seismic interval. And you can also benefit from the structural constraints, so the presence of faults, if you've interpreted them or if you've got them into PaleoScan, to constrain the geometry of your model to create some consistent geometries. And I've not insisted on this in this presentation, but you can also, in the model, generate first geometries, as you can see in this tiny example up there. Then this type of model, even if you're not considering faults, also has the advantage of creating some synthetic geometries and disregarding potential polarities that are going to cut across the stratigraphy, cut across the sedimentary deposits, or some lateral change in polarities that are going to be induced by, for example, vertical artifacts, like, for example, underneath these bright spots that I've presented. It can be also the case with a coal bed, as I've been saying in the presentation already. So if you get a coal bed, it may induce for one given seismic surface of deposition, one geological surface of deposition. It may induce a lateral change in the polarity that PaleoScan, with the automatic propagation, may not detect or may not image properly, and that may require a lot of manual interpretation. So in this case, if you're just using the marked only faulted method for this, you can just constrain your geometries by marking the reflectors above your coal bed deposit, for example, and below and laterally. And then PaleoScan is just going to use these geometries that you've marked to cut across the coal bed, disregarding the polarities induced. So eventually, when you're going to create some horizons or horizon stacks and mapping some attributes, you're going to preserve a mapping that is not going to be biased by wrong geometries, induced by the fact that PaleoScan would have linked one given polarity, not caring for the lateral change of phases. As well, again, so I've talked about the injectites and the relevance of using it if you've got some igneous intrusions. Again, those are intrusions that are going to cut across the stratigraphy. So, for example, with dikes and with the igneous intrusions. And eventually, it's quite basic, but it may be useful, quite basic case if you've got some low amplitude seismic intervals. For example, if you're going towards your basement, you're going to lose energy in your reflections, in the reflectors, or if you've got some noise or chaotic intervals, if you want to get rid of the artifacts, then you can also use this method for these parts. And of course, because we're not opposing the two type of models that we have available in PaleoScan, then you can think of relevantly and smartly combining the two to create some consistent structures over the whole seismic interval. And this is the type of the tiny animation that is shown here. So yeah, thank you very much for your attendance, for your interest. And again, this session is going to be available in video on demand after this presentation.